Good day, everyone. Today, we're going to be talking about infrastructure-agnostic machine learning workload deployments, which basically means how to deploy your machine learning workloads to multiple cloud environments and to deploy it on-prem with just one deployment setup. Abby and I will be giving this talk. Abby and I together work at Maven Code. So, a little bit about us. We work for Maven Code. Maven Code is an artificial intelligence solutions company located in Dallas, Texas. We do product development, training, consulting around provisioning scalable data pipelines in the cloud. We do deployment of machine learning models on different platforms and in different cloud environments. And we do a lot of things around streaming, IoT, edge device application development as well. So, a little bit about us. My name is Charles Aditloy. I'm a machine learning platform engineer at Moving Code. I've been doing this for the past 15 years, building large-scale distributed application. And with me today is Abby. Abby, you want to introduce yourself?
And my name is Abby Akudun. I'm a machine learning and data science consultant here at Maven Code. I have experience building and deploying large-scale machine learning models across different industries and different verticals like healthcare, finance, telecommunications, and insurance. So in terms of agenda today, we'll start by going through an overview of a machine learning model deployment workflow. Next, we talk about the various approaches to model training and model deployment in the cloud. After that, we'll go ahead and talk about how we can deploy machine learning workloads in the cloud. We'll talk about implementing feature storage backend, basically for machine learning model training. And we'll talk about how you can run containerized Spark ML workloads on Kubernetes with QFlow Pipeline. Overview of machine learning deployment workflow. When you deploy machine learning models, the first aspect to this has to do with getting your data. You source the data from different locations. And next thing is when this data comes, it doesn't come prepared, it doesn't come ready. So you have to do some kind of pre-processing. So you have a data, some parts of this data, like you have skewed data, you have missing data points. You want to do some pre-processing to get the data ready for machine learning. After you're done doing some pre-processing where you look at missing values, look at things like outliers, then you go to the next stage, which is feature engineering. So during pre-processing, if you run into issues in terms of your data, you want to fix those processes and you want to create features for those from your data. Once you have your feature ready, then you can go to the next stage. It is where you actually do the model training and your model evaluation. In model training, this is where you apply different algorithms, and this is where you look at different metrics. After you are satisfied and you pick which of the models you think is good for model deployment, you go to the next stage, which is where you want to use the model for actual inferencing and scoring, as well as model management. And also, once you have gone through this entire pipeline, you are ready to push your model for inferencing. In terms of this machine learning workload deployment, you can have all these steps that we've put together right here, the pipeline. You can do this either on any of the clouds, like Google Cloud, AWS, Azure, and this also can be done on-prem. In terms of efforts for machine learning model deployment, so your data verification as when you do your data preparation and storage. Also, after you've gone through the data preparation and storage and you've gone through all the different processes that we've talked about, then you talk about your model inferencing, your model monitoring, and this is where you need efficient compute resource management. In terms of the workflow as well, data sourcing usually takes 16% based on experience from what we've been doing over time. Then the pre-processing part of this takes at least 32% of the time. And your feature engineering piece is like 10%. The model training itself and the model evaluation takes about 36% of your time. Then the scoring and management is only about 2%, and the model inferencing is about 4%. A typical machine learning developer workflow is what we're trying to show here. Like we said, we have a pipeline. You start from data sourcing, you go to pre-processing, you go to feature engineering. So all these data sourcing, the pre-processing and feature engineering, all these, once you get your features, you can put your features in a storage location. And that's where we have things like S3, like Google Cloud Storage and Azure Storage. That's where they come into play. In this case, you have a transformed data that is ready to be used downstream by the data scientist. And you store this data with the derived features in a storage location. Once your data is in the storage location and the data is prepared, then we can talk about model training. The model training, the model evaluate, the model scoring and management, as well as inferencing, this can all happen in a cloud environment. The data scientists, the ML engineers, they work hand in hand in terms for pulling the data and get the data process before you start ML training on a managed cloud service.
Yeah, thank you very much, Abby. So just to illustrate a lot more better with what Abby just said, a typical developer learning workflow looks just like this. You have your storage where the data is, and you're trying to wrangle the data, pre-process the data, and make sure the data is ready for ML training. And you have the compute environment where you run a lot of all this your compute workload. So if we look at all the steps that Abby mentioned previously, the data source and the pre-processing, you can handle that on the cloud by putting your data on things like S3 bucket, Google Storage bucket, and Azure Storage buckets. And your data can come from different sources, streaming data from message queues or databases or even from another bucket. So once we have all this data processed and we have it in a form where we can do the feature engineering and the data is ready to do the ML model. There are different options out there right now in terms of managed services on Google Cloud. I mean, you have you have the Google Cloud AI, you have the SageMaker, and you have the Azure ML. So, as a machine learning engineer or a data scientist, you have all these options across all the different clouds that you can use. So, depending on your skills and what you do and how you do things within your enterprise, you may be boxed to one of these options and things like that. So, this is just a view from the perspective of just a single ML engineer. So, if we look at it from the enterprise at the enterprise level, where you have multiple data scientists and multiple teams doing things in different ways, it looks a little bit more chaotic, especially now when there's a multi-cloud strategy in most organizations where you want to make sure you have all the major cloud providers, you want to have your on-prem and things like that. So the question is like, how can we make things a lot more better and not have a kind of workflow like this? And that's why we started looking at ways of building a cloud agnostic deployment that basically allows us to run on any of the major cloud providers or on-prem. So imagine you have multiple data scientists working on different things, and a lot of times they're sharing data or pulling data, and all of the data scientists are connecting to all these data stores and trying to pull the data to like train a model, and they can decide to just train their model with Google Cloud AI or SageMaker or Azure ML and things like that. It becomes it becomes highly unmanageable. So to solve this, we started looking at how we can simplify things. And the major things that we saw around ML training is like you have the compute, which is where you do your training, and you do this and the storage. So most of the time, implementing machine learning, it becomes a little bit expensive because of the cost of compute and the cost of storage and things like that. So our goal was to see how we can simplify this thing, especially if you have multiple cloud environments across multiple things. We thought about abstracting our compute workloads to run on Kubernetes. And our ML workloads, we thought about building everything on feature store so that no matter where the data is coming from, if we can build it up and have it in a feature store, every data scientist or every ML engineer on the team can go pick up the features they need, and they can use the compute on the Kubernetes environment. So going back to that workflow again, so imagine where this is what we have, where you have your storage, you have your compute, and we go in We pull all this data, we run a compute on them, and we try to get a result. So um, instead of having it that way, why not let's have a kind of cloud neutral deployment where we can abstract a lot of things that we're doing such that our storage can be seen to the data scientist as a feature store. They don't have to go through all the process of like pre-processing the data, getting the data from all the source, and combining the data or doing aggregation and things like that. Can we expose the data to them just as a feature store? And when they want to deploy, instead of worrying about like all the underlying infrastructure on Google Cloud or Azure or AWS, can we deploy the workloads on Kubernetes? So the question is like, why the need for cloud agnostic infrastructure? So for us, it makes it easier to migrate our workloads. So sometimes you're doing something on a particular cloud environment. So let's say Azure, you want to move it to JKE, to Google Cloud, or you want to move it to AWS. So the migration was a lot more easier for us, especially since we do a lot of consulting in this space. We have multiple clients with different cloud providers, and we want to be able to shift the workloads across all these cloud providers. And the fact that we're not tied to a particular cloud infrastructure stack makes it easy for us to like try new things and experiment a lot more easily. And it's easier for us to implement best practices. So basically, our solution is portable across all the major cloud infrastructure and on-prem. So we can establish best practice patterns around building a feature store, around deploying models, around model serving and things like that. And one of the things that this provides is a common base denominator for all enterprise ML work, especially in an ML environment where you have an hybrid of all these different cloud infrastructure and things like that. But the overall benefit is to control cost because you can basically forecast your demand, estimate your demand. You're not running on a managed service where you don't really understand what's going on behind the scenes and stuff like that. But you can with the kind of deployment we have, you can easily manage your utilization, know what people are doing, know when things are like bootstrapped and how long they're gonna be on and things like that. So a cloud agnostic ML environment that we work with looks like this. We have a feature store. We're using Apache UD to build our offline feature store. And one of the reasons that we work with Apache UD is like it's basically allows us to like combine historical and fresh data that are coming into the store, and we can basically combine it into one and basically write it out into the cloud. UD backs up into Amazon S3 bucket, basically most of all the cloud infrastructure storage buckets, so you can use it with Google Cloud or Azure storage as well. And once we basically have our feature store, we have Kubernetes set up. Most of the time, we can use a managed Kubernetes, or you can set your own Kubernetes up. But the fact that we're running on Kubernetes allows us to like package our model training into containers that can connect to this feature store to grab the data and use it for the training. So that's on a high level the kind of abstraction that we have and we run. So what's the feature store all about? So feature is a measurable, observable attribute that is part of an input to a machine learning model. So let's say you want to train a model, and before you train your model, you need some input. So you have the feature vector that represents all the attributes that goes inside your model. I mean, your algorithm for model training, and over time you can have as more data set comes in, you can have more and more features coming in for your model training. So features are derived from like your raw data store. It could be like let's say a user table. It could be a streaming data source from IoT, or it could be like aggregates of inputs, or it could be something that you basically compute over windows of time, like every 5 minutes. Tell me the number of people that basically clicked on a particular item, or hourly or daily and things like that. So you have your feature vector that you compute and you fit into the model for your model training. So, and future changes over time, and over time, as you have more feature, you may want to retrain your model once you see that your models are drifting. So you have the time components, you have all these features flowing into your model where you use it to train your model and things like that. So the advantages of having a feature store includes for us is like it makes it easy to operationalize our ML workflow. Most importantly, the data management and storage of the data for our models. Featured can be shared easily among teams running different models and pipelines, and we get to version our data sets and track changes easily. And in terms of like consistency between the input attributes that we use for training and the models having. Basically, if you have everything in the feature, especially in online feature cases, feature store, you can basically use the same attributes that you're using for your model training, and you can basically use it to enrich your input that you use for in your inferencing. So there are two types of feature stores. Mainly, the first one is the offline feature store that you use for like batch training, and you have the online feature store where you use that for inferencing. So you basically use it to enrich the input data that the user is sending to inference, and you basically before you send it to the model and do your inferencing and things like that. So we're gonna draw a lot more on the offline feature store, which is where we do a lot of ML training. So we have, let's say we have a streaming and batch data source coming in. We have we basically use a QFlow pipeline to basically orchestrate the inflow of data. So once the data comes in, we'll try to write it to our feature store, which is basically Apache UD sitting on any of the major cloud providers. So we have a configuration for the feature store built with UD. So the data flows into our pipeline, and once the data flows into our QFlow pipeline, we bootstrap our Spark operator that basically writes the data at the end of it to the UD storage system. So why did we choose UDI? The need for a unified platform where new data can be made available in addition to the historical data within minutes. So every time, over time, you keep acquiring data. It could be an IoT application, it could be a database where you're adding more users and stuff like that. So one of the main challenges before UDI was like, how do you reconcile the new data that you're getting with the old data without having to recompute the old thing all over again. So UDI solved that problem for us. So that's one of the reasons why we're using UDI. And if we need to do a quick computation, because we can have a Spark job that basically runs and computes, basically we extend the data frame, we can add more column, compute and derive the values that we want to do, put, and we can just write it back to UDI. Then incremental versioning of our feature collection. So one of the things we need to do sometimes is like you want to go back in time and basically maybe retrain your pipeline or basically retrain your model to try to see what's going on. So the fact that Hudi has a timestamp on all these rows allows us like just do a time travel in terms of how we query and whenever we want to like run a model training on new data sets or historical data sets to do some experiments and things like that. And it backs up into Azure, Google, and AWS cloud storage layer. So with that, we ensure portability of our data sets across all the major cloud providers. And of course, we do a lot of things with Spark and PySpark, so it makes our life easy working with Udi. So getting data into Hoodie feature store for us is done mainly with QFlow Pipeline, where we have these stages in QFlow Pipeline. So QFlow is it's a toolbox that runs on Kubernetes that allows you to do a lot of ML training and model training on Kubernetes. So for us, we basically use QFlow to orchestrate a lot of all this process. So let's imagine in this case, we have a Kafka data streamer that connects with Kafka data store. So we have a component that will connect to the data store to pick up the data. It will connect to the topic, um, to connect to the Kafka server, pick up the data. And once we pick up the data, one of the things we try to do is to like validate the schema. So we try to like run a validation to make sure that the data we're getting matches what we're expecting. Depending on the condition, in some cases, we may need to drop the data sets In some cases, we need to like assume a default value if the data is not there. So we run a validation and we create a schema that maps to the data set that came in. Then the next thing we do is to do the pre-processing, which is we might need to transform the data into a new form to make sure that it's in the format that we want to like write in our data store as a feature. So in this case, once we've done the pre-processing and the transformation, we now write it to the UD table where we just have it as a data frame that we write into the UD feature store. So we do a lot of all this orchestration with QFlow Pipeline. And just to like focus a little bit more about our Hoodie writer, this is what it looks like. We connect to a feature store. We create a Spark session. We make sure we have all the packages that we need. We do some configuration. Basically, the Hoodie options. We have some configurations in there for the write, and we do a write inside the data store. We write a data frame. In this case, the data frame will contain all the features that we want to write, and we just do an input write, and we specify the format as an UD table. So that's how everything looks on a high level. So our platform looks like this. We have a feature store where we have the data sets that the data scientists can consume. And once they consume the data from the feature store, they want to run their ML workloads with it on Kubernetes. And because it's Kubernetes, that's the common denominator. You can run Kubernetes on AWS, on Azure, or Google Cloud. And that means you can basically run your workload, your ML jobs on any of the major cloud providers as long as you can containerize it. And you can auto scale your Kubernetes node pool and things like that. So for us to run machine learning machine learning workloads on Kubernetes, we're leveraging an open source project called QFlow that basically allows you to run ML workflows on Kubernetes. Basically, it's a toolbox with a lot of things that you can use to run your workloads on Kubernetes. So it has these operators. So operators are things that helps you manage the deployment of your components on your containers on Kubeflow. You can basically manage the life cycle of a particular deployment by monitoring things and making sure things are deployed successfully. So there are different kinds of operators on Kubeflow. There's a TensorFlow, the PyTorch, the XGBoost, and the Spark operator, of course, which is gaining a lot of leverage right now, and it gets bundled with the QFlow deployment. So on a high level, the cloud agnostic ML machine learning development environment in a typical enterprise looks like this. You may be running on Azure or AWS or Google Cloud. It doesn't matter as long as you have Kubernetes. And your Kubernetes will contain a bunch of CPU node pools or GPU node pools if you're doing things with GPU. And you have the Spark up, you have Kubeflow that basically allows you to like deploy your machine learning. The Kubeflow that allows you to like run your machine learning tool, your machine learning component. So you can have, and Kubeflow has a bunch of operators. For us, we do a lot of things around the Spark operator. So a data scientist or an ML engineer will just need to like whip up a Jupyter notebook and run their Spark jobs, and the whole life cycle of their job is controlled within their namespace on Kubernetes, and that means they get allocated a certain percentage of resource within that namespace, and they can run their job easily within that namespace. And you have other operators as well, like the TensorFlow operator, depending on what you're doing, if you're doing things with TensorFlow or a PyTorch operator. So from there, we can connect to our feature store, which is our prepared data sets. And basically, we can use it to run our ML models and things like that. So on a good day, the workflow for a typical ML developer on our team looks like this. You write your PySpark code or your Spark code. You containerize it. And once you containerize it, you create a Spark application YAML, which is the CRD that defines how your Spark job is going to run on Kubernetes, and you just do a kubectl apply, and that deploys the job to the Kubernetes cluster. So once your job is deployed, for you to deploy your job to the Kubernetes cluster, so it looks kind of like this, where um, you come in there, you do a kubectl apply, you submit your jobs, and once you submit your job, you have your Spark driver running in a container, and you have your executors running in their own containers as well, and everything is all coordinated because you're using the Spark operator, and all these runs on Kubernetes, all containerized, running on Kubernetes, and any of this can be on cloud, it can be on-prem, it can be on your local laptop, or as long as you have Kubernetes, you can easily do that. So what you need to do is to just come in and do a kubectl apply, and you basically deploy your Spark workloads on the Kubernetes cluster. So now imagine you have multiple people from different teams trying to basically run their ML jobs. So, and they're using the Spark operator or TF operator. We have the underlying infrastructure, which is Kubernetes. It can auto scale. And basically the Kubernetes cluster can be on Amazon, Azure, Google Cloud, or on-prem, or wherever you have it running. And all these teams can now come in and deploy their jobs, and depending on the configuration and what they're trying to do, some people may be running a 3-node cluster, which is like you have 3 executor containers and 1 driver container. Some people may just have 2 executors or 2 executors and 1 driver and things like that. But the fact is, like, you have a shared resource where everyone can come in and deploy their job, and you can monitor the life cycle of its jobs as things are going, and things like that. So it doesn't matter what kind of, what you're doing. We have a common base, and everybody's doing things the same way across the enterprise. So a little bit more details around the YAML file for the deployment. So the Spark application YAML file basically allows you to specify the configuration of the Spark job that you're trying to deploy. So in this case, we're trying to deploy a Spark application for clickstream analysis. That's the ML job we're trying to run. So you deploy the job in a particular namespace. So let's say they've created a clickstream dash jobs namespace. And so that's where the job is going to run, and that's where the job is going to reside. So we have a container that contains the workload, what we're trying to deploy. And we have a Python file baked inside that container that contains a PySpark code. And we're saying, like, we want to run with PySpark 3.1.1. And we have different policies around it, depending on how you want to kick off the job. If something fails, in this case, we're saying that if the job fails, we'll try to retry 3 times, and and the interval between retries is like 10 and things like that. Then you specify the number of drivers, which is typically 1, and the resource allocation to the driver. Same thing with the executor. In this case, I have 1 driver and 1 executor, and I have all this configuration. So this is all I need to submit a new job that will run my ML job in a Kubernetes environment, run it with Spark operator enabled. So we might decide to just make things a little bit more fancy, where we want to connect to the feature store, and we want to be able to split our data set into train, test, split, and we want to fit in the training data to the Spark ML operator or ML container that's going to run a Spark training job. And we have a test data that we use for evaluation after that, and we can basically do some predictions when the whole thing is done. So we can pipeline these, and that's where we use QFlow Pipeline to orchestrate this whole process, where we have a feature store reader that basically connects the feature store that contains all the attributes and all the data sets that we need for the model training. Then we feed it into the training test plate, and those are components that we've implemented, and the QFlow pipeline components. So just to delve a little bit deeper, the DSL, which is the domain-specific language for describing the QFlow pipeline that deploys the job, kind of looks like this, what we have on the right. So you specify the DSL, um, and the DSL basically creates the graph that you saw in the previous slide. And you have all these components. In this case, we have a feature store reader component that goes in and reads data from the feature store. We have a train test splits data set that basically takes whatever we got from our feature store, the output of it, which is going to be in packet format, and it does a split, and you specify the split ratio, zero point 0.8 and zero point 0.2, zero point 0.8 for training and zero point 0.2 for testing, and it's going to execute after the feature store reader. So basically, the first thing we do is to connect to the feature store, get the data sets, export it in a packet format to a storage location, and we now do train test split on the data sets. Then once we've done that, the next thing is to we basically create a staging area for the training data, and we now do our ML training on the clickstream data that we've prepared for training. So and for that, this is a YAML file on the right that basically contains the information that we saw in the previous slide. So we're basically trying to deploy this resource. So you use a resource up DSL on the QFlow pipeline. But if you notice, this YAML configuration is similar to what we saw previously. So we're trying to run a Python type code, which is, it goes without saying, it's a PySpark job with Python 3. This is our base image, the image pool policy, and stuff like that. Then we do we run our training, and once we run our training, we specify the number of drivers, the drivers and the executors. In this case, we're running with just one driver, and we've bumped things up to like 3 executors.
Thank you, Charles, for that detailed overview of how we do infrastructure-agnostic machine learning workload deployment here at Moving Code. Next, we're going to talk about cost comparison with managed cloud services on AWS. In terms of compute utilization, managed services running on AWS, they go around like 100% utilization. Then your QFlow plus UD feature store takes about 30%. When you're talking about startup time, managed services running on AWS takes about 66 seconds, but QFlow and UD feature store on AWS takes about 15 seconds. In terms of team agility and productivity, we have about 6 times productivity for both QFlow and plus UD feature store compared to AWS. In summary, then on GCP, if you do a similar comparison on GCP, you can see we have a 26% utilization cost for QFlow and UD feature store. For QFlow plus UD feature store on Google Cloud Storage, in terms of startup time, we have about 12 seconds. In terms of team agility and productivity, we have 6 times productivity. In summary, we have a simplified common deployment of ML training process across multi-cloud and on-prem infrastructures. After the initial the learning curve and the overall team efficiency improve significantly. Teams are not logged into a particular cloud infrastructure. With this, with what we have described here today, you are free to go with any of the cloud providers. And also it is easy for you to control costs. At the same time, it's much easier for you to forecast your future capacity for demand capacity. Thank you very much.